Hi, my name is Salama Al-Labban and I will talk about moment-curvature relations. The purpose of this project is to develop software to analyze and plot the relation of curvature. Reinforcement concrete structures are designed to fail under an overload condition. After a structure is designed for safety, it is checked to assure that it will perform in a satisfactory manner under surface conditions. The beam will crack under surface load if the tensile stress in the concrete exceeds the bending strength of plain concrete. After formation of cracks, the steel carries the tensile force needed to support the applied load. The crack beam can continue to support increasing load until the ultimate capacity is attained due to compression failure of the concrete. There are three principal stages of behavior of beams. The first stage is the beam is uncracked, then the beam is cracked but the stresses are within elastic range, and the final stage is the beam reach its ultimate strength. In the first stage, this figure shows the relationship of the first stage. It shows the cross-section and transport section and strain distribution and finally stress distribution. The strain will be linear and the stress also will be linear in this stage. It assumes that there is complete bond between the concrete and the steel, which means that the steel and concrete experience the same strain, provided the maximal tensile stress in the concrete is less than modulus of rupture. The tensile stress in the steel bars is greater than the tensile stress in the concrete at the same depth because the steel has a larger modulus of elastic. Because the steel and concrete experiences the same strain, the relation of the stress equal to modal ratio, which this ratio is the ratio of the modulus of elastic of the steel to that of concrete. For ordinary state strength concrete, this ratio will be 8. For the purpose of analysis, the steel bars can be replaced by an area of concrete equal to NAS. The stress in the steel is N times the stress computed using the Bendix formula, with a value of y equal to the distance from the natural axis to the depth of the steel. The second stage is the cracking, elastic section. When the maximum tensile stress in the uncracked beam reach to the modulus of rupture, the concrete will be cracked. Cracks are assumed to extend from the tensile face to the natural surface, which is the same as assuming that the concrete below the natural surface has zero tensile strength. After cracking, it is still assumed that the plane section remains plane, so that there is still a linear strain distribution through the depth of the beam. For analysis, the steel is replaced by an equivalent area of concrete equal to NAS, so that the cracking transfer section will be as shown in the figure. This figure will show the cross-section at cracking and how to transfer the section for analysis. The strain distribution will be also linear and stress distribution will be linear. And the distance between the compression force and tension force is JD. When the crack develops, there is a sudden increase in the maximal stress in the concrete and steel. The compressive stress in the concrete can be replaced by an equivalent compressive force, C, passed through the center of the concrete can be stress distribution, and the stress in the steel can be replaced by a tensile force at the center of the steel. Another equilibrium condition is equal summation of m equal to 0. By using this equation, we can estimate the location of the natural axis and how to calculate the moment and curvature. Under surface load, normally designed flexural members will be in this cracked and elastic condition. The maximal stress in the concrete and steel will depend on the bending moment procedure by the applied load. In actual structure, the bending moment varies along the length of the beam, and so the maximal stress in the concrete and steel will also vary along the length. As the bending moment increases above the cracking moment, the natural axis remains at the same location, and the steel stress is less than Fy. When the concrete stress goes beyond the linear elastic range, the natural axis moves toward the compression phase. However, the strain distribution through the depth is still assumed to be linear. In the last stage, the behavior of the beam will be ultimate strength. This figure will show the cross-section at the crack and how distribution of strain, which will still linear, and the stress distribution will be non-linear. The relationship between the strain and stress at the concrete will be linear when the strain from 0 to epsilon naught, which equal to 0.002, and will be linear from 0.002 to 0.003. For steel, the relationship between the strain and stress will be linear from 0 to epsilon y, and after that will be constant the relationship. As the bending moment is increased further, the natural axis moves further toward the compression phase. This occurs when the strain at the level of the steel reaches to epsilon y. The bending moment can be increased until the maximal compressive strain in the concrete reach the assumed limiting value of 0.003. The balance of forces establish the location of the natural axis, which will be C, and the ultimate moment equal to ASFYZ, where Z is the distance between the tensile and the compression force. At this stage, the concrete undergoes compressive failure, and the beam is no longer able to be supported the applied moment. We can analyze and plot the relation between the moment and curvature by using one of these programs. We can use Excel or Java or Fortran or MathCAD Prime 3. In my project, I used MathCAD program to analyze the relation between moment curvature and plot this relation. I will show the program how to write this equation and how to get the result. This program of MathCAD Prime 3. Assume the beam will be rectangular with width B and H and D from the center of the steel to the top of the beam. Input variable will be width of the beam equal to 15 and height of the beam will be 32.5 and effect depth of the beam will be 30. Strain used in Hognested model will be 0.002 and sigma C max will be 0.003, and factors used in Hognested concrete stress strain model will be equal to 150. AS will be 6.24, ES to 29 million, and FC prime will 4,000 and FY will 60,000, and number of sites will be equal to 7. This will be the first stage cracking point, and calculate IG by using this program and FR and UT and EC. The result of the moment crack and curvature crack will be 1.4 and 8.097, this relation. For the stage 2, this equation will be rho ISBD and N ESEC and C will be 11.213. The result will be MY 819.382 kips in foot, and curvature will be 1.065. In the last stage, we used many equations to calculate the compression force and tension force for the nonlinear relationship. For compression will be C equal to various volume X. And by using this equation, the C will be 7.715. And to check, compression force will be equal to tension force. The result of the moment and curvature will be Mn equal to 858.187 kips foot and phi n 3.889. Now how to plot the result. We input the volume of phi and the moment, and this relation will be plot between the moment and curvature. Now we will take another example to check my work. Let's use B equal to 12 and H equal to 34 and D 21, AS equal to 3. The result will be very fast. For cracking point will be M crack 91.39, 5 crack 7.74. For the stage 2 steel yield, MY will be 278.015 and 55.1.47. And for stage 3 for concrete failure, the volume of C will be 4.636 and Mn will be 292.518 kips foot and 5n point equal to 6.471. And the plot relationship will be like this. This is the end of my project. Thank you for watching my video, and goodbye. Thank you.